the first problem, consider f of z equal to 1 minus cos hz by z square. Now I'm keeping the 1 by z square outside, and what is the series expansion of cos hz? It is 1 plus z square by 2 factorial plus z power 4 by 4 factorial plus etc. So when you simplify this, you get 1 will get cancelled, and there is a 2 fact z square outside, and there is you can cancel it with all the powers. So basically you get minus of 1 by 2 factorial plus z square by 4 factorial plus etc etc. Okay. Now this shows that if you let limit z tends to 0, so now if you find limit z tends to 0 f of z, if you calculate this limit will, if you calculate, so this all these higher powers will be 0, you will get only minus 1 by 2 factorial. Okay, so we saw in the definition of removable singularity, if limit z tend to z naught f of z is some finite quantity, that means that it is a removable singularity. Okay, therefore 0 is a removable singularity of this function. Okay, so let's continue. Since it is a removable singularity and the limit z tend to 0 f of z is minus 1 by 2 factorial. So if you define at z equal to 0 minus 1 by 2 factorial for z not equal to 0, the function as it is, this will be an entire function. Okay, because the only singularity is 0, and the singularity we are define it suitably to make it an entire function. And by the definition, the coefficient of 1 by z will be the residue of the function f of z at 0, but there is no 1 by z term in the Lorentz series expansion of this function f of z. Therefore the residue of the function at 0 is 0. Okay, let's see one more let's see a next example. E power 1 by z. So e power z has series expansion summation x z power n by n factorial, but in place of z we have 1 by z. Okay, so we substitute 1 by z here, we get summation k equal to 0 to infinity 1 by n 1 by k factorial. Why all these things should be changed to k, 1 by k factorial z power k. Okay, now if you noticed in this series expansion of e power 1 by z, there are infinitely many negative terms, therefore it is an essential singularity. Again, what is the coefficient of 1 by z power k? It is 1 by 1 factorial, that is 1, therefore residue is 1. Now if you look at f of z equal to z power p times e power 1 by z, suppose some z power p is given in front, still it will have infinitely many negative terms. Okay, therefore even for z power p times e power 1 by z, 0 will be an essential singularity, whatever p is a natural number, any integer will also do. Okay, now let's look at the third example. Suppose f of z equal to z square by 1 minus z. Okay, one, so we look at the behavior at 0. Now 1 by 1 minus z, 1 by 1 minus z equal to 1 plus z square plus etc. So if you multiply this 1 by z square inside, we get 1 by z square plus 1 by z plus etc etc. There are only finitely many negative terms, therefore 0 is a pole. Okay, we have expanded 1 by 1 minus z around the point 0, z minus 0, z minus 0 the whole square, so we are talking about the singularity 0. Okay, if you want to talk about the singularity 1, then you have to expand everything in the powers of z minus 1 whole power n. Okay, so that is a different thing. Now here we are talking about the at the point 0, so we get p2 is not equal to 0 and all the higher coefficient are 0, so we get 0 is a pole of order 2. Okay, okay, let's look at f of z equal to z square by sin z. All these things are uh, all these questions are asked in previous year CSA problem, you can have a look at it. Now the denominator vanishes, sin z equal to 0 if and only if z equal to k times pi. Okay, now these zeros are simple zeros. Okay, means 0 of order 1. Why? Because if something is a something is a repeated 0, then that suppose then that will be a 0 for the derivative also. but this k pi, if you substitute in cos z, cos k pi will be minus 1 whole power k. Okay, that won't be 0. Therefore, these numbers are not 0 for the derivative of sin z. Therefore, these are all simple zeros of the denominator. Okay, we take zk to be k pi for all k belongs to z. Then, since these are all simple roots of the function sin z, we can write sin z as sin z equal to z minus zk times fk of z. And since it is a simple 0, means 0 of order 1, zk won't be a root of this function fk of z. Okay, if zk is root of this function, again one more z minus zk can become outside from this, so we get zk will be a root of order 2, at least 2 for sin z. Okay, okay, so we get sin z equal to this expression. Now we deal with k equal to 0, k will not equal to 0, both the case differently. Suppose k equal to 0, then k pi will be 0. Let's see whether let's calculate this limit z tend to 0 f of z. If this is a finite, then it is a removable singularity. Okay, now we calculate this limit z tend to 0, z square by sin z. Now sin z will be z times f0 of z. Okay, for zk, it is z minus zk times fk of z. When k equal to 0, it is z minus z0. Z0 will be 0 times pi, it is 0. So z minus 0 times f0 of z. Now this is equal to limit z tend to 0. So this z and this z square, one z will cancel. We get z by f0 of z. Okay. Now limit z tend to 0. Numerator is 0, but denominator is not equal to 0 because of this condition. Fk of k pi is not equal to 0. In particular, f0 of 0 pi is not equal to 0. Therefore, it is a finite quantity. Numerator goes to 0. Overall 0. Therefore, we get limit z tend to 0 f of z, limit is 0, that means that 0 is a removable singularity. Very good. Okay, now let's look at k not equal to 0 case. In this case, uh, again we look at the limit z tends to k pi f of z. uh, this is equal to limit z tend to k pi z square by sin z. Again, since by our result, sin z equal to z minus k pi times fk of z. Okay, and so we get limit z tend to k pi, this 1 minus z minus k pi term I am taking it outside, I get z square by fk of z. Okay, now this fk of z, k pi is not a root of fk of z. Okay, therefore no more z minus k pi will come from this side. Therefore we get this is equal to limit z tend to k pi 1 minus z minus k pi into some function, but this is equal to infinity. Okay, so because at z tend to k pi, this will be k pi square by fk of k pi, it will be a finite quantity. Okay, therefore, and this goes to infinity. So infinity into finite, overall it will go to infinity. So limit z tend to k pi f of z goes to infinity, means that k pi is a pole, or there is a only one z minus z, or there is only one negative term is appearing here, therefore it is a pole of order 1. Okay, okay, let's continue. Left f of z equal to e power z by 1 minus cos z. Now let's see whether the limit z tends to 0 f of z, whether it is exist or not. So yeah, like in general, like if it is exist and finite, it is a removable singularity. 0 is a removable singularity. If it is infinity, it is a pole. If it doesn't exist, then it is a essential singularity. That's what we saw in the beginning. So now I claim that 0 is a essential singularity. So for that I have to show that this limit doesn't exist. To show this limit doesn't exist, I approach 0 in two different directions. I'll get two different answers. Okay, now I'm going to approach in the real line. So I consider this function as a real function. So I take f of x equal to e power x by 1 minus x. Okay, and this x by 1 minus x, I define it separately as x by 1 minus cos x. G of x equal to x minus 1 by cos x. Now, this is the graph of the function f of x equal to this is the graph of the function cos x. Okay. Why? Because cos 0 is 1, cos pi by 2 is 0, cos pi is this is minus 1, cos 3 by 2 is 0, and so on. Okay. It is a function of periodicity 2 pi. Similarly, this is a sine function. Okay. Graph of the sine function sine x. So better to remember the graph of sine x, cos x, tan x, sometimes cosec, sec x, cot x also. It will be very helpful. So this is sine 0 is 0, sine pi by 2 is 1, sine pi is 0, and so on. Again, it is a periodic function of period 2 pi. Now we calculate the we calculate the right limit of this function g of x at the value 0. So what we want? We want limit x tends to 0 plus x by 1 minus x. That means that you are approaching 0 from the right side. Okay. Then numerator will be 0 because as x tends to 0 plus x will goes to 0. As x tends to 0 plus cos will goes to 1. Right, cos is as x tends to 0 plus it goes to 1 because cos 0 is 1. So basically it is a 0 by 0 form. So you can apply L'Hospital. So you get 1 by cos x differentiation is minus sin x. So minus of minus sin x we get sin x. So we get limit x tends to 0 plus 1 by sin x. Okay. Now if we approach sin x from positive side. Okay, sin x from positive side, you are approaching 0 from positive side in the sine curve. So you are getting positive values goes to 0. Okay, so positive value goes to 0. It is like 1 by n sequence. So the answer is infinity. Now therefore we conclude that so the right limit of the function g of x at 0 is infinity. Okay, this is the g of x. Now f is f is nothing but e power this function. Okay, but now if this goes to infinity, e power that also. If this goes to plus infinity, it's e power that also goes to plus infinity. Okay, so we get f of 0 plus will be infinity. Similarly, we calculate g 0 minus. So basically you are approaching x from the left side, 0 from the left side, and calculating limit x by 1 minus x. Again this is 0 by 0. So now again 1 by sin x. Now you are approaching 0 from left side. Okay. So now 0 we are approaching 0 from left side in the sine curve. Now these are all negative numbers because it is value is negative numbers. So it is like minus 1 by n. So you are approaching to 0 through negative numbers, and the negative numbers getting smaller and smaller. So basically this is reciprocal of negative. So it is reciprocal of negative numbers goes to 0. So it will goes to minus infinity. Okay, basically it is like minus 1 by n sequence. As n tends to infinity, it goes to minus infinity. Now if this goes to minus infinity, then this goes to 0 because e for minus infinity is 0. Therefore the same function when x tends to 0 from the right side, the value is infinity, but when x tends to 0 from the left side, the value is 0. Therefore, but if it is a finite if it the limit exists, then whatever way you approach the limit, the answer should be same. But we are getting two different limit, therefore 0 is an essential singularity. This is a different technique from what we saw in the previous problem. That way I choose this problem. Okay, this is using completely using limit. Okay, so similarly we see variety of techniques in each of the problems. Let's consider f of s equal to sine of 1 by cos 1 by z. Okay, again cos z equal to 0 if only if z equal to n pi plus 1 by 2. So you have to remember all these numbers when cos 0, when sine is 0. If you remember the graph, then it is you can easily remember. For example, see these are the points at which cos curve n is. That is precisely n pi by 2 plus n pi. Okay. Okay. Now cos 1 by z equal to 0 if z equal to 1 by n by plus pi by 2. Okay. Now if you look clearly, 0 is a singularity of this function, because at 0 the function is not defined, but this sequence is converges to 0. 1 by n pi plus pi by 2 as n tend to infinity goes to 0. Therefore, in any neighborhood of 0, one other, in whatever small neighborhood you draw around 0, one you at least one other singularity will also be there. Singularity of this form will be there. Actually, there will be infinitely many such singularity will be there. Therefore, 0 is a non-isolated singularity. But all, so 0 is a non-isolated singularity, but these things 1 by n pi plus by 2, they are all non-isolated singularities. Okay, so I mean, in this problem you have to say about z equal to 0 only, and one of the option was 0 is a non-isolated singularity in the CSA problem, so you have to choose that option. Okay, you can prove that these are all non isolated singularities, and actually uh, they will be like we okay, they are all essential singularity. Yeah, so even for this function also it will be an essential singularity. We will see why in the next problem. Now we see look at the function f of z equal to cos of 1 by z. At z not equal to 0, we want to know the behavior, so we just expand the series expansion. So this will be the uh, Lorentz series expansion of this function in a annual region about 0. Then you see there are infinitely many negative powers of z. Therefore, 0 is an essential singularity. Again, uh, okay, let's see. We could look at f of z equal to sine of cos 1 by z at z not equal to 0. Uh, we just saw that 0 is an essential singularity of cos 1 by z. Okay, for this function, 0 is an essential singularity. By Cassarati-Weierstrass theorem, if 0 is an essential singularity of a function, then at any neighborhood of that point, any deleted neighborhood of that point, if you look at its image, it will be a dense subset of G. Okay, let me phrase again. Suppose 0 is a essential singularity of a function G, then any deleted neighborhood of, then you look at the image of any deleted neighborhood of 0, it will be a dense subset of C. Okay. Therefore, since 0 is a essential singularity of cos 1 by z, any deleted neighborhood of 0, uh, if you take the image, it will be a dense subset. Now, sin z is a non-constant entire function. Okay. So, if it is a non-constant entire function, it will, you can prove that it maps a dense set into a dense set. Okay. Therefore, sin of G of, so G is cos 1 by z. So sine of cos of B of 0 comma the deleted neighborhood of 0 is again a dense subset. Okay. So if it is a dense subset, means that sine of sine composition G. Okay. What is sine composition G? So basically sine composition cos of 1 by z. Okay. Therefore sine of cos of 1 by z has 0 as an essential singularity. This is a very different technique. From that you can observe that if if something is essential singularity of this function, when you compose it with another entire function, the result will be still entire function. I mean, sorry, the result for the resulting function also, the number will be still essential singularity. The proof, the same argument. Okay, think about it. Now let's look at f of z equal to e power z minus 1. Now the denominator vanishes if e power z equal to 1, but e power z equal to 1 if and only if z equal to 2k pi I. Okay, again we deal differently. If k equal to 0, then this 2k pi I will be 0. Now 0 is a root of e power z minus 1, but 0 is not a root of its derivative. Okay, it's e power z minus 1, the derivative will be e power z, but 0 is not a root of e power z. Therefore 0 is a simple root of e power z minus 1. Okay, therefore similarly 0 is also a simple root of z. Okay, so simple root of this and simple root of this means basically e power z minus 1 can be written as z times some another function f of z. The numerator you will have some z. and this f will not vanish at f of 0 not equal to 0. Okay, if 0 is a simple root of e power z minus 1, then e power z minus 1 equal to z times f of z such that f of 0 is not equal to 0. Therefore, this z will cancel, we'll get only 1 by f of z, and this f not vanish at the point 0. Therefore, for 1 by f of z, 0, for 1 by f of z, 0 is not a pole. Okay. Therefore, we conclude that for 1 by f of z, 0 is not a pole, means that for this function, 0 is a removable singularity. 0 is a removable singularity because this f of z is equal to 1 by h of z, where h of z is not equal to 0. Okay, that is the reason. Okay, basically, if numerator and denominator have a 0 of same order, then like you can basically cancel them, and the answer will be removable singularity. Okay, let's continue. Again, if k not equal to 0, again same argument. If 2k pi I is a root of e power z minus 1, 2k pi is not a root of its derivative e power z. Therefore, 2k pi is a simple root of e power z minus 1. But 2k pi, in case of 0, 0 is a root of both numerator and denominator. But in case of 2k pi I with k not equal to 0, it only is the root of the denominator only. So, and it is a simple root for the denominator. Therefore, it will be a pole of order 1. Yeah, so let's see. So 2k pi is a also 2k pi is not a root of the denominator, only it is a simple root of the, 2k pi is not a root of the numerator, but a 2k pi I is a simple root of the denominator. Therefore, it is a pole of order 1. Or a simple pole. Okay, let's look at f of z equal to z power 5 by z cube plus z. So if it is a polynomial, we have some standard method. Let's see. So first you can cancel one z. Okay, you'll get z power 4 by z square plus 1. Therefore, you can talk about singular is at I and minus 1. Clearly, I and minus 1 are isolated singularities. Now we'll look at the we look at limit z tend to I, z minus I times this function. Okay, and let's see what we get. We get limit z tend to I in z square plus 1 is z plus 1 and z plus I and z minus I. So z minus I will cancel. You get z power 4 by z plus I. Limit z tend to I, z power 4 by z plus I will be I power 4 will be 1. I plus I, you will get 2i. So you get 1 by 2i. Right. Therefore, limit z tends to I, z minus I times f of z is a finite quantity. Okay, let's see what we learned when we were looking at the poles. Okay, just a minute. Yeah, so limit z tends to z naught, z minus z naught whole power k times f of z equal to finite quantity only if k equal to m. Okay, so for larger k and lesser k, you will have always different value. So limit z tends to z naught, z minus z naught whole power k times f of z, you will get finite value only when this k is the pole of only if k is the k, only when k matches with the um, order of pole of z naught. Okay, only if z naught is a pole of order k, at that time only this limit will be finite. Therefore, we conclude that therefore we conclude that this limit is finite, means that I is a pole of order 1. Okay, similarly you can argue that minus I is also a pole of order 1 or a simple pole. Okay, let's look at one more problem. So again, this is the same idea. Cos z by z square minus 1. You look at limit. So now the possible now the singularities are 1 and minus 1. So you calculate limit z tend to 1 z minus 1. The limit is finite. Therefore, 1 is a pole of order 1. Similarly, limit z tend to minus 1, z plus 1 times f of z is a finite quantity. Therefore, minus 1 is a pole of order 1. Okay, therefore 1 and minus 1 are simple poles of f of z. Okay, so these are all different techniques. So pretty much we cover all the techniques used to find the singularities in this lecture. Okay, f of z equals z power 5 by 1 plus z plus z square plus z power 4. Now z power 5 minus 1 equal to z minus 1 into 1 plus z square 4 z square plus z cube plus z power 4. Sorry for the typo. Yeah, z cube z cube plus z power 4. Okay, let w be a primitive fifth root of unity. That means that if you take all its powers, w power 0, w power 4 up to w power 1 up to w power 4, this will give you all the fifth root of unity. Okay, now 1 is a root of this factor, therefore the root this w square, w cube, w power 4, they will be root of this factor. Okay, therefore this factor can be, this polynomial can be written as z minus w into z minus w square, z minus w cube into z minus w4. Okay, again you use the limit argument. Okay, limit z tend to w, z minus w times f of z. You will see that this z by z minus w will cancel with the z minus w in the denominator of f of z. We left with only these factors. Okay, and z w is not a root of none of these factors in the denominator. So when you substitute, when so limit z tend to w, this quantity you just substitute w, but w is a fifth root of unity, so z power 5 will be 1, and in the denominator we get w minus w square, w minus w cube, w minus w4. So this is a finite quantity and this is 1, therefore w is a pole of order 1 because this limit exists and a limit exists as a finite quantity. So similarly you can see that w square, w cube, w power 4 also simple roots. Okay, okay, let's continue. F of z equal to sin z by 1 minus tan z. Now this function has two types of singularities. Okay, first uh, sin z is equal to, sorry, tan z equal to sin z by cos z. Okay, so wherever cos z is 0, at that point this function is not defined, so they are all singularities. Then whenever tan z equal to 1, at that point also denominator becomes 0, so that is also a different set of singularities. Okay, now first we deal with these singularities at which the function is not defined. I mean, like the at which the cos z is vanishes. So now I look at limit z tends to n pi plus pi by 2 f of z. Okay. Now 1 minus tan z is 1 minus sin z by cos z. That is cos z minus sin z by cos z. So this cos z will go above. We get limit z tends to n pi plus pi by 2 sin z cos z by cos z minus sin z. Now when limit z tends to n pi plus pi by 2, cos z will be 0. So numerator will be 0. In denominator, numerator will be 0. In denominator, this is 0. You will get minus sin n pi plus pi by 2. That is a finite quantity. Okay. So this new denominator goes to finite, numerator goes to 0. So overall it goes to 0. Okay. So if limit z tends to z naught f of z exist, means that these points are all removable singularity. Okay. Okay. Now again we have to look at the points where tan z is equal to 1. So tan z equal to 1 if and only if z equal to n pi plus pi by 4. Okay. Tan pi by 4 is 1, that you guys know, but tan is a periodic function of period pi. Therefore for all if you add n pi to pi by 4, for all those numbers tan z will be equal to 1. Now these are all simple roots of tan z. Uh, Tan z minus 1. Again you can look at the uh, you can look at the derivative of tan z. For the derivative n pi plus pi by 4 is not a root, so it is not a root for the derivative, means that they are all simple root of the function tan z minus 1. Now again, this n pi plus pi by 4, they are not root of sin z. Okay, sin z equal to 0 if and only z equal to n pi, but it is n pi plus pi by 4. Therefore, for numerator, uh, this quantity n pi plus pi by 4, they are not root of the numerator, but they are simple root of the denominator. Therefore we conclude that, these they are all simple poles. Okay, if they are a simple root of the denominator, and if they are not roots of the numerator, then we can conclude that they are poles of order 1. Okay, so some exercises I would like to point out. F of z equal to e power cosec of 1 by z. F of z equal to z by e power 1 by z minus 1. F of z equal to z times 1 minus e power 1 by z, and you know at what point you have to look at the behavior of the singularity. So I mean at 0 at 0 at 0 you have to check this behavior. Okay, okay. So I have looked at many books to come up with some simple way of finding the singularities. So if you like this video, please like this video and share it with others also, and you subscribe to my channel. uh, Thank you. If you have some doubts, please let me know in the comments. Thank you.